17, 18, and 19 are the last three chapters. What I'm going to do is I'm going to go out of order, though. I was thinking about this. I'm going to go 17, then 19, and then 18. Because what I want to do is I want to do 17 acid-base. I'm going to talk about acid-base reactions. And then 19 is redox. So I'll talk about redox reactions. And then 18 is chemical equilibrium, which we'll talk about. Kinetics and equilibrium. We'll talk about at the very end. So did I already talk about this slide? All right. The most comprehensive definition is Lewis. Lewis acids are electron pair acceptors, Lewis bases are electron pair donors. However, that's not the easiest. The easiest is Bronsted. Bronsted, we're going to miss some acids, we're going to miss some bases. Like, carbon monoxide. Carbon monoxide is not a Bronsted base. Bronsted bases are proton acceptors. Carbon monoxide is not really a proton acceptor. But carbon monoxide is electron pair donor, it's a good one. So carbon monoxide is a powerful Lewis base. So we're going to miss some of those, but it'll make our life easier. And in fact, this chapter doesn't really talk about Lewis. This chapter is focused on Bronsted. If you look at the title of this chapter deals with proton transfer. So Lewis acids are proton donors, H+. Lewis bases are proton acceptors. So this is pretty much Bronsted, the Bronsted definition for acid-base reactions. Let's take a look at some reactions here. Arrhenius is just H+. Arrhenius acid. Arrhenius base is OH-. That's too narrow of a definition. I already talked about this, right? Yeah? Okay, so let's take a look at a Bronsted acid-base reaction. Here we have ammonia and water. Ammonia and water. Ammonia is the base. Bases take the H+. This is going to form ammonium and hydroxide. All right, is that a favorable reaction? We have to determine the driving force. In order to determine the driving force, we want to do this. We want to imagine this reaction going backwards. And if we go backwards, what's the acid, what's the base going backwards? So going forward, this was the base, this was the acid. Going backwards, which one's the acid, which one's the base? So the acid loses the H. Which one loses H? The ammonia or the hydroxide? Ammonium loses the H. So this is the acid going backwards, and hydroxide gains it to form water. And so this is the proton donor, this is the proton acceptor, the reverse. And so we can label it. This is the base, this is the acid, this is the acid, and this is the base. Then we compare, which one's stronger. The way we're going to compare the strength is by the acid-base strength chart. The acid-base strength chart is given here. Like this. And so we can compare ammonium versus water. Okay, here's ammonium. Here's water. So ammonium is a stronger acid than water. Okay, then we can compare the bases. When we compare the bases, we're going to compare hydroxide and ammonia. So the bases are on the same chart, and here, but it's inverted, it's flipped. So the strong bases are down here, it gets weaker. So here's hydroxide, up there's ammonia. So hydroxide is more powerful. Over here, ammonium's more powerful. So the strongest acids are at the top left, the strongest bases are at the bottom right of this chart. You can see here, the strong acids are up here, the strong bases are down here. This is because of the conjugate relationship. Did I talk about the conjugate relationship already? Yeah. So if the acid's strong, the base is very weak. Because the base doesn't have a strong attraction for H+. If the acid's weak, the base is strong. The base has a very strong attraction for H+. So the base doesn't want to let go of it. Okay. So that's how we're going to figure out the driving force. So let's take a look at some more reactions here and then see what we got. Okay, that's bronzite. This is a different type of reaction here. This is a Lewis acid-base reaction. BF3 can't get an octet. Why can't it get an octet? Because fluorine's never going to double bond, right? Fluorine's only gets a single bond. And so in order for BF3 to get an octet, fluorine would have to double bond, which it doesn't do. The lone pairs are missing here, unfortunately, but there's lone pairs on there, but there's no lone pair on boron. So boron has less than an octet. One way to get an octet is if it reacts with an electron pair donor, like ammonia. And so this is an example of a Lewis acid-base reaction. BF3 is an electron pair acceptor, so this is our Lewis acid. Ammonia is our Lewis base. Ammonia is also a Bronsted base as well, but BF3 is not a Bronsted acid. BF3, in order to be a Bronsted acid, it will have to have an H that it could donate. It doesn't have any H donating. And so in this case, we got electron pair that's going to be shared, donated, and we form this boron-nitrogen single bond. So everybody has an octet. Now what happens here is the formal charges change. So boron's going to be -1, nitrogen's going to be +1. And so essentially nitrogen's donating an electron to boron, but that's okay in this case because boron wants an octet. So Lewis acid-base reaction. What we're going to focus on are Bronsted acid-base reactions. Bronsted acid-base reactions have a hydrogen that's being transferred. So if you look at this hydrogen is attached to the A. Over here now the hydrogen is attached to the B. A has lost it. And so this is our proton transfer. The base takes the hydrogen. It's not a neutral hydrogen, it's a hydrogen ion, which we call a proton, H+. So the base takes the H+. Since it's positive, it's going to make this whole thing positive. And since it's losing a positive, it's going to make this negative here. Now, when we're looking at the driving force, we look at the forward versus the reverse. Now, let's see which side's more stable. Okay, over here, in the last reaction we looked at, we're going from weaker to stronger. Stronger is less stable, so this is uphill. This is an uphill reaction, and so there's no driving force. In order for there to be a driving force, it has to be downhill. We're going from stronger to weaker, that's downhill. This is going from weaker to stronger, it's uphill. But it depends on how steep it is. This one's fairly steep, but it's not so steep that nothing can make it up there. And so if you have a big pool of ammonia and water down here, some of those ammonia and water molecules will have enough energy to climb all the way up here and react to form ammonium and hydroxide. And so what we say is ammonia is a weak acid. Weak acids partially hydrolyze water. And so a little bit will react to form the ions, ammonium and hydroxide. This is why we saw ammonia and water metathesis reactions. We treat ammonia and water metathesis reactions as if it were ammonium hydroxide. You guys remember doing that? You should review that too for the final. And that's because a little bit forms. And that little bit is enough to react in metathesis reactions. Let's take a look at this next reaction here. This next reaction, we're taking CH3COOH. What's that called? Well, there's another way of writing this formula. The other way of writing this formula is H, this acidic hydrogen here, HC2H3O2. HC2H3O2 is also called acetic acid. So we take our acetic acid and react it with water. Water is interesting because water can either act as an acid or a base. In this case, it's going to act as a base. The bases are going to take the hydrogen. So the water is going to take the proton from acetic acid to form hydronium over here, and acetic acid is going to lose the proton to form acetate over here. Now let's see, is this reaction going to be downhill or is it going to be uphill? And so when we're going to compare, we are going to reverse this reaction and then look, who's the acid going reverse? hydronium or acetate? Who loses the hydrogen going backwards? Hydronium. So hydronium is the acid and acetate would be the base. Okay, then we're going to compare the two acids, acetic acid versus hydronium. Which one's stronger? And so what we'll do is we'll just consult the chart. This chart is on Piazza. So there's hydronium here. The strongest acids are top left. So we go hydronium to, do you see acetic acid? CH3COOH. CH3COOH is acetic acid. So is this uphill or downhill? It's uphill. So we're going from weaker to stronger. Stronger is less stable. And so this is uphill. So we say there's no driving force, but it depends on how steep. And it turns out that a little bit can make it up. You know, not much, but a little bit. That little bit, we say that weak acids partially hydrolyze water. That is, weak acids partially react with water to form the ions. So that's what we're going to have. Just a small fraction of these will be able to react. But it's not like we're going to get a lot of reaction, like it's going downhill, this is going uphill. Tritium is radioactive. Yeah. Tritium, well, hydronium is with a 3 down here.
Yes.
H3O plus. And this hydrogen can be any isotope hydrogen. Tritium is going to have a 3 up here. Like that. So the nuclear symbol for tritium is this. And tritium is radioactive. And so you can make radioactive hydronium if you use tritium. You can put all 3 hydrogens as tritium, or maybe 1 tritium and 2 regulars. So 1 tritium, 2 regulars, and an oxygen. You know, that. So you could do it. So it's the hydrogen itself. So when we're looking at a chart like this for acid and base strength, we only need 1 chart basically because of this conjugate relationship. This is called a conjugate relationship. So perchloric acid is the strongest, and its conjugate base is perchlorate when this loses an H+. So if this is very strong, this is very weak. So we'll have this inverted relationship here. So what we're going to do is we're going to look at other pairs. So what is the conjugate acid of ammonia? Did I cover this already or not yet? No. So ammonia is, well, a conjugate acid. So that means ammonia is the base. And so what's the acid that's linked with ammonia or paired with ammonia in this case? Well, if ammonia is the base, then there are 2 ways to get it. One way is we could just look at the chart. And so we look for ammonia as the base, which is here. So if ammonia is the base, then its conjugate acid would be ammonium. The other way of doing that is, what do bases do? Bases gain an H+. If ammonia gains an H+, it forms ammonium. Ammonium is the acid. And so these are going to be seesaw. You know, let's say ammonium is kind of weak, therefore ammonia is a little bit stronger. But, you know, when I say weak, it's not terribly weak. Let's take a look at next one here. What is the conjugate acid and conjugate base of bicarbonate? So the conjugate acid means that bicarbonate is acting as a base. Bicarbonate is unusual because bicarbonate is amphoteric. It can either act as an acid or base. The prototypical amphoteric substance is water. But bicarbonate also does it, just like water. Water can go either way with equal ease. Bicarbonate can't. You know, it favors one way over the other. Oops. Do that. And so what is the conjugate acid of bicarbonate? Well, the conjugate acid means that bicarbonate's acting as a base. And so if bicarbonate's the base, then what is the acid? Yeah, if bicarbonate's the base, then carbonic acid is the acid. Or CO2 in water. Carbonic acid is not stable. If bicarbonate's the acid, then the base is carbonate. And so we either add an H or lose an H to figure it out. If we don't have the table. So we could go here and take a look. The conjugate acid, and so this is called a conjugate acid-base pair. The acid ammonium, the base ammonia. And so the way we read this is the conjugate acid of ammonia is ammonium. Or we could say that the conjugate base of ammonium is ammonia. They're just conjugate pairs. Same thing here. The conjugate acid of bicarbonate is carbonic acid. The conjugate base of carbonic acid is bicarbonate. A bicarbonate can go either way. So the conjugate base, so now bicarbonate's acting as the acid. Bicarbonate is the acid, it loses H plus and forms carbonate. So this is the conjugate base of bicarbonate here. The conjugate relationship. So this is back from the electrolyte chapter. Strong acids are strong electrolytes. They ionize completely or hydrolyze completely. Weak acids are weak electrolytes. They slightly ionize. Depends on the driving force, how steep the hill is. For strong acids, it's all downhill. For weak acids, it's uphill. And depending on how steep it is uphill will dictate how much ionizes or hydrolyzes. Strong bases, they have a strong attraction for protons. This is strong Bronsted bases. Weak bases have weak attraction for protons. Strong bases hydrolyze water completely. Weak bases partially hydrolyze water. And so I'm going to draw these hydrolysis reactions a little different here. Rather than drawing them as ionization, we'll draw them as acid-base reactions. And so for HCl, that's one way of doing it. The other way of doing HCl is this. HCl plus H2O liquid goes to hydronium plus chloride. Then we look for the driving force for this. When we look for the driving force, HCl is going to be the acid, water is the base. How about going backwards? What's the acid, what's the base going backwards? Yeah, the acid is H3O plus, and the base is Cl minus. Okay, then we look for the driving force. And so we're going to compare the two acids and compare the two bases. So when we what's that? Yeah, this chart's going to be on the test. So HCl versus hydronium, which one's stronger? HCl, so we're going stronger to weaker. If we're going stronger to weaker on one, it's going to be stronger to weaker on the other because of the conjugate relationship. So water here will be a stronger base than chloride. Is that correct? Yeah, that's correct. Water is a stronger base than chloride. Here, lower down on the right. And so what that means is this is downhill. If it's downhill, that means that there's driving force. And so what we get is we get complete ionization or complete hydrolysis. Ionization reactions written like they did, and this is a hydrolysis reaction written like this. Well, let's take a look at a weak acid like they had up there earlier. When we look at a weak acid like acetic acid here, so they wrote acetic acid the normal way, HC2H3O2, and reacted with water. And so in this case, acetic acid is the acid, water is the base. So we're going to have a Bronsted acid-base reaction, which is going to form hydronium and acetate. And then when we go backwards, I already asked you this, hydronium is going to be the acid, acetate is going to be the base. Now let's compare the strength. Did we already compare the strength? Okay, we're going to compare acetic acid versus hydronium. Well, I see hydronium's here. Where's acetic acid? Down here. So which one's stronger? Hydronium. Hydronium's stronger. Acetic acid's weaker. And the same thing, water versus acetate. There's water there. Acetate's here. Acetate's stronger. It's always going to be like this. It's always going to be strong, strong, weak, weak, or weak, weak, strong, strong. Always. So which way is the driving force? That way. Driving force is backwards, so what we say is there's no driving force. But it depends on how steep this is. It's an uphill climb, therefore there's no driving force. But what we know is that not all the molecules have the same energy. There's going to be a small fraction of molecules that are going to be quite energetic. Energetic enough that they can climb this and react. And so it turns out in both these cases, let's say if I have let's say 10,000 molecules, out of that 10,000, maybe 1 or 2 have enough energy to react. And so we get small amount of reaction. And so this is why we say that weak acids partially hydrolyze, because there's a small fraction that can actually make it up the hill in this reaction.
Why is the driving force going that way for this one, and for that one it's going this way?
Because we want, the driving force is stronger acid to weaker acid. But this is going weaker acid to stronger acid.
So why does the DF point that way then? Or why does the DF point just react?
Yeah, because actually what this arrow is pointing to is the downhill direction, energetically. So the arrow is pointing forward because things are going to roll downhill. If I'm here, the arrow is pointing backwards because it's going to roll downhill. And so if there are molecules that come up here, well, they're going to come back down here. We're going to get no reaction. You know, there's just going to be a small fraction of molecules that can react up here. But even this small fraction, what happens is this. Even when these react to form hydronium and acetate are an unstable combination. If a hydronium sees an acetate, they're immediately going to react because it's a strong acid, stronger base. They're immediately going to react and roll back downhill. But the situation here is you got this pool of molecules that are in constant motion. So even if these two react, what happens is they'll fall back down here, but a new pair will come and react and take its place. And so that's continually happening as we're cycling through. This is called the dynamic equilibrium. This is in chapter 19.
Should we be cautious about the way we put our arrows?
Yes. Yeah, here there's no driving force. So I say, normally what we do is this. If I drew the arrow backwards, then I could say driving force there. But if I drew the arrow forward, there's no driving force here.
So would that be no reaction?
This would be no reaction. But I say no reaction. When I say no reaction, it's this. It's 99.9. This is 99.9% reaction. 99.99% no reaction. But there's a 0.01% population that has enough energy to react. And so since it's 99.9%, 99% no reaction, we'll call it no reaction, but that doesn't mean a little bit can't react and a little bit does react. And so this is why we say weak acids partially hydrolyze with water to react. Now it depends on how weak the weak acid is. The stronger the weak acid, the more reaction. The weaker the weak acid, the less reaction. So acetic acid has about 99.99% no reaction.
So whenever you have a strong acid and strong base with the products, is the arrow going to point towards the reactant?
Yes. Yeah. A stronger. Yes. All right, this is the chart from the book. The difference here is there's some differences in the ordering. Our chart had perchloric at the top, they have HI, and then there's some other differences here. Our chart is more updated than this chart here. And our chart has a bit more recent data than this chart. The other thing they do is they knock off the H+. Do you see that? And And so then we'll just show the base here. That's it. This has a little bit more descriptive stuff here. These bases, the conjugate bases of the strong acids are so weak, we don't really consider them basic. Let's take chloride as an example. Chloride's a base, according to this chart. So if you have sodium chloride would also be a base. Let's say you ran out of antacid, and you wanted some antacid. Could you substitute table salt? Because sodium chloride's a base. Could I use table salt as an antacid? Is that? No. The reason is because chloride is so weak, we call it neutral. It's not really a base at all. And it's so weak, it doesn't really hold on to the H+. This is why we have 100% ionization, because chloride does not hold on to the H+. It's got to be weak. If chloride gripped onto the H+, then this would not have 100% ionization going forward. It wouldn't dissociate completely. The stronger the base, the more it's going to pull on that H+. And so something like hydroxide has a very strong pull on H+. So once hydroxide grabs onto the H+, it forms water. Does water lose that H+ easily? No. It's stuck on there. So that's part of the conjugate relationship also. And so here's just a question of list the following acids in order of decreasing strength. Strongest first. So this is hydrogen oxalate ion, ammonium, and phosphoric acid. Which of these three do you think is the strongest? Yeah, phosphoric acid. You'd be right. And then these two, maybe ammonium. Yeah, those two would probably just need to consult the chart. So let's just look at the chart here. We're going to look at the acids going down the list. Here's phosphoric acid comes in first. Here. And then let's look for hydrogen oxalate. And then, well, here's ammonium. But hydrogen oxalate is not on this chart. Do you see it? No. It's missing from our chart. So it's missing from our chart. Let's check the book's chart. So looking at the book's chart, here's phosphoric acid, here's hydrogen oxalate, and here's ammonium. So you're right. Strongest, phosphoric, next hydrogen oxalate ion, last ammonium. This is just using the chart to find the species. One of the other things you should notice about the chart of amphoteric species can go either way, like water. Water is going to occur as a base over here, and it's going to occur as an acid down here. There are other species that are amphoteric. Hydrogen oxalate ion is amphoteric. And so hydrogen oxalate occurs as an acid here, and it occurs as a base up here. So it occurs on both sides of the chart. Now, how do you know? Is hydrogen oxalate going to act as the acid, or is it going to act as the base? You don't know until you see what you react it with. It's the same thing with water. Is water going to act as the acid, or is it going to act as a base? Well, it depends on what you react it with. And that's going to dictate how it behaves. And so this is all about predicting acid-base reactions. We have this thing here. Predicting acid-base reactions, we want to go downhill. So for acids, we want to go from stronger acid to weaker acid. And that's downhill. But you know, the base chart is inverted. And so on the base chart, we want to go uphill in a way. Because going uphill, we're going from a stronger base to a weaker base. But overall, it's going to be downhill. You know, stronger to weaker. That's our driving force. That's what we're looking for. If we're going from weaker to stronger, that's not a driving force. That's not what we're looking for. And so this chart we're going to come back to later. But let's take a look at doing reactions here. And so I'm going to do this reaction, and then we'll set another one up. This reaction is kind of a composite between net ionic and ionic and complete. So we're going to take hydrofluoric acid. What's the formula for hydrofluoric acid? That would be hydrochloric, HCl. Hydrofluoric would be HF. Hydrofluoric acid and sulfide ion. What's the formula for sulfide ion? SO3 2 minus. That's right. All right. When we have an acid-base thing, we got to figure out which one's going to be the acid, which one's going to be the base. Can you tell? Which one's going to be the acid? We do, but we haven't put the products yet. Yeah. This is going to be the acid, and sulfide must be the base. In this case. And so what we're going to do is we're going to transfer an H plus from the acid to the base. And so A is going to lose an H plus. If it loses an H plus, what are we going to be left over with? F or F minus? We're going to be left with F minus. And then SO3 is going to gain an H plus, so we're going to form HSO3. What's the charge on HSO3? Minus. That would be it. Okay, now what we're going to do is we're going to reverse this. And when we reverse this, who loses? Well, the acid loses. Which one is the acid? HSO3 loses, and this gains. Okay, now we compare. We want to compare the acids versus the bases. And so we're going to go back to our chart here. And we're going to compare HF versus HSO3 minus, which is not on this chart. We're going to have to go back to the books chart. Sorry. So HF versus HSO3 minus. So HF is here, HSO3 minus is here, and therefore we're going from stronger to weaker. And because of the conjugate relationship, it's got to go strong, strong to weak, weak. So SO3 2 minus must be a stronger base than F minus. See that? Because they're connected. HSO3 minus goes to SO3 2 minus, HF goes to F minus. So it's going to be flipped. So strong, strong to weak, weak. Is this downhill or uphill? This is downhill, so we got driving force for this. So this reaction should occur. All right, what we're going to do here is this. We're going to make a more general procedure for this. They're talking about redox and acid base. We aren't going to talk about that because we haven't gone through redox. Redox is actually chapter 19. And so we're going to do more acid base reaction examples. And so the example next I'm going to do is I'm going to do sodium hydrogen sulfate, or sodium bisulfate. What's the formula for sodium bisulfate? Yeah, sodium bisulfate in solution. NaH NaHSO4 NaH2. Yeah, actually it's going to be like this. That's the sodium ion, and bisulfate is HSO4 charge minus. And so it's just NaHSO4. All right, plus sodium hydrogen carbonate, or sodium bicarbonate, call it. So what's the formula for sodium bicarbonate? NaHCO3. NaHCO3. So when we do this, if we do a metathesis reaction, metathesis is just swapping the ions. So if we swap the ions, we're going to form sodium bicarbonate and sodium hydrogen sulfate, or sodium bisulfate. And so there's no reaction for metathesis here. But just because there's no reaction for metathesis doesn't mean there's no reaction. We should look for other potential reactions. And so we're going to look for other potential reactions. Well, the first potential reaction we should look for is a Bronsted acid-base reaction. And so let's take a look for a Bronsted acid-base reaction. So when we do Bronsted acid-base reactions, the first step is we're going to inventory. Inventory means what are the major species we have in solution. And so when I inventory this, I have sodium ions and bisulfate ions. And then I have, well, sodium ions and bicarbonate. I already have sodium there, so I'll just add bicarbonate here. And then there's one other species that can act as an acid or a base in Bronsted acid-base reactions. Do you know what other species is present in this? Not hydrogen. There's no hydrogen. Water. There's water present because these are solutions. And water is both a Bronsted acid and a Bronsted base, so we're going to have to factor that in. Now, when we look at it, did you see sodium ions on the chart? Are sodium ions good proton donors, proton acceptors? No. Sodium, they don't have any H to donate, so we're going to call it N for neutral. Now, bisulfate, what is bisulfate? So if we look on the chart here and look up bisulfate, I see it. It's an acid. Here. Do you see it? It's an acid. But you have to be careful when you use this chart. So we inventory, this is our inventory. Then we ID acids, bases, and neutral species. Acid, bases, and neutral species. And so sodium is a neutral species. Bisulfate is an acid. But you have to be careful because bisulfate is also a base. If you take a look at the top right here, you see here, bisulfate occurs on both sides of the chart. And so it's an acid and a base. Bicarbonate's the same thing. It occurs on both sides of the chart, and water is the same thing. It occurs on both sides of the chart. So I have 3 acids and 3 bases. Which one? Will all of them act as an acid, and will all of them act as a base? No. Which one? The strongest. And so what we do is we take the strongest acid and strongest base. Okay, so we'll take the strongest acid and strongest base and then transfer one H. Transfer an H plus. And so out of these 3 acids, which is the strongest? Bisulfate, bicarbonate, or water? Yeah, bisulfate's the strongest. And so bisulfate's going to be the acid. Which base is the strongest? So I need to scroll down.
Water? Carbonate? Bicarbonate?
It looks like bicarbonate. You see bicarbonate, and then water, and then bisulfate. And so bicarbonate's going to be the strongest base. And so our acid is going to be HSO4 minus. Our base is going to be HCO3 minus. Now what's going to happen is the acid's going to lose an H. So if the acid loses an H, we're left with SO4. What's the charge on SO4? 2 minus. And then HCO3 will gain an H to form H2CO3, charge is neutral. H2CO3 is unstable, that's going to form H2O liquid plus CO2 gas. But we'll just leave it there so we can see it. So these are our products. Now if we go backwards, who gains, who loses? So that's the base. This carbonic acid loses. That's the acid. Now what we're going to do is we're going to look for the driving force. So I need the driving force. So for driving force. So we got to determine which way is downhill, forward or reverse. So we're going to compare the 2 acids, bisulfate versus carbonic acid. Which one's stronger? So I have bisulfate here and carbonic acid here, CO2 and water. Which one's stronger? Yeah, bisulfate's stronger. So we're going from stronger acid to weaker acid. Therefore, there's driving force. The bases have to follow. That means bicarbonate must be a stronger base, sulfate's a weaker base. So bicarbonate's a stronger base, sulfate's a weaker base. So that follows. And so we got driving force. But so the reaction that's going to occur is this here. This is the reaction. It's going to be in net ionic form, like that. Let's try one more. These here. Didn't make it to pH. So didn't quite finish chapter 17. There's still one more section. Let's do this one. We're going to take solid sodium sulfide and react that with sodium chloride. All right, so what's the first step in Bronsted? So we're going to inventory. And so sodium sulfide is going to consist of sodium ions and sulfide ions. Sodium chloride consists of sodium ions and chloride ions. So we already have sodium ions here. And there's one more species present. Water. Water is a very weak acid and a very weak base. So oftentimes it's ignored, but you shouldn't ignore it because sometimes it's not the weakest, even though it's very weak. Let's ID the acid, bases, and neutral species. Sodium ions? Neutral. Sulfide? No. Sulfide, we'll see it on the right. Do you see it here? Sulfide is a strong base. And so this is a base. Chloride is a base, but it's very weak. It's almost neutral. Water is both an acid and a base. So we have 3 bases and 1 acid. So since there's only 1 acid, it's got to be water as the acid. But which of the bases do we pick? The strongest, which would be sulfide. And so the reaction here, if there's a driving force, we don't know if there's a driving force, but the reaction should be sulfide plus water. Sulfide's the base, water's the acid. That's going to form what? Well, what we do is we just transfer 1H. Transfer 1H. So if we transfer 1H over here, we're going to get HS minus. And this loses an H, so we're left with OH minus. So we just transfer 1H. Now, when we go backwards, which one lost? HS or OH? HS lost, so that's the acid, lost a proton. OH gained a proton. This is the base. Okay, now let's compare the 2 acids. Water versus HS minus. Which one's a better acid? It's actually here. Water versus HS minus? Water. That's our driving force. That means sulfide must be a stronger base than hydroxide. Is that correct? If it isn't, then we made a mistake. Sulfide is stronger than hydroxide, so that's correct. We have driving force. So the reaction was not between sodium sulfide and sodium chloride. The reaction was between sodium sulfide and water. Sodium chloride is just a spectator in this. All right, okay, we're out of time, so I'm going to stop here. But these are examples of Bronsted acid-base reactions. Have a nice Thanksgiving.